Can you hear us now?
Okay, now it's okay.
Please,
Yes, it's okay.
oh, now it's okay. Okay, thank you very much. Sorry for the issue.
No problem.
So,
Right.
okay. Sorry for technical problem. But as can I say, we classify the private keys in three main categories. We have the illegitimate access, where the unauthorized party is being the access to sensitive data, the unwanted notification, where a possible attacker can tamper or falsify and profile the data, and the data disappearance, where the data can be profiled and can be deleted or profiled log or
Excuse me, Marco. There's no sound again. Hello, can you hear me?
Can you hear me?
Okay.
I do not hear you.
Hello, can you hear me? I'm going to share my screen. Can you see the slides? Can someone say something? Michele, can you see the slides?
Yes, yes, yes. I see the slide.
Okay.
Okay.
Good morning, everyone. My name is Parinaz Tavari, and today I will be presenting our paper titled Invisible Threats: Rethinking Privacy in Digital Healthcare. This work is part of our research at the University of Salerno, and it focuses on the evolving challenges and approaches related to privacy in modern digital healthcare systems. The digital transformation in healthcare has revolutionized the patient care and system efficiency. And with tools like EHR, CDSS, and telehealth, information flows more easily, but also it becomes more vulnerable. The more our systems depend on data, the more we must safeguard individual privacy, and especially as AI models also require massive data input. With vast volumes of sensitive data being collected, the potential for misuse or leakage is growing. Laws like GDPR and HIPAA exist, but compliance doesn't always mean safety. There's a need to reassess how we protect privacy in systems that weren't originally designed with today's modern technologies in mind. In our research, we aim to map the landscape of privacy measures and risks in digital healthcare, and we organized our review around 4 research questions exploring core concepts in identifying threats, investigating models, methods for secure data sharing, and reviewing applicable regulations. Our methodology combined database searches, primarily PubMed, with manual search in Google Scholar and citation chains. We focused on publications from the last 10 years to ensure relevance. We used keywords and mesh terms tied to digital health and privacy with related terms. Screening was conducted in 2 stages: first title abstracts, then full text, and we excluded articles that didn't directly address healthcare privacy concerns. In total, we analyzed 59 papers and 9 web sources and then categorized the resources to answer our research questions. Also, in the whole phase, Zotero was used for structured reference management. Privacy, security, and confidentiality are often used interchangeably, but they actually differ. Privacy is about control over data, security involves mechanisms to prevent breaches, and confidentiality is an ethical obligation. All are crucial to trust and usability. Informed consent is fundamental, and patients must know how their data is used, especially for research. GDPR emphasizes the right to access and also control one's data. Ethics approvals ensure responsible data handling and build public trust. Access control is a cornerstone of digital privacy. RBAC limits access based on roles. ABAC extends this to attributes like time and location. And mandatory access control and discretionary access controls are 2 distinct approaches to access control in computer systems. MAC enforces strict, also centralized privacy policies, while DAC discretionary provides more flexibility by allowing resource owners to control access to their resources. These frameworks help tailor access while keeping records secure and also traceable. Audit trails track who accessed what and when, enabling accountability. Shared access, for example, for elderly patients, raises usability and security issues, and some systems allow patients to generate their own pseudonyms to retain data control and trust. AI also possesses new threats. Even without direct identifiers, inference attacks can extract sensitive attributes. Telehealth introduces risks during online consultation due to weak encryption. By membership inference attack, or MIA, means revealing the inclusion of data point in a dataset or training set of an machine learning model. PHI can be leaked unintentionally through AI models or machine learning. Genomic data is very hard to anonymize. Even if only a part of someone's genome is available, genotype imputation, which is a technique, can reconstruct more of their genetic profile, increasing the risk of re-identification. In big data settings, we must ensure data collection and processing respect ethical standards. Sharing data for research must be balanced with robust privacy mechanisms. Privacy-enhancing technologies, or PETs, can be architectural, algorithmic, or augmentative. Examples include federated learning, differential privacy, or DP, and synthetic data. Choosing the right PET depends on data, use case, and risk profile. As you can see, DP is a system for sharing data while protecting the privacy of individuals within that data. It works by adding random noise to the data in a way that obscures individual information, but also preserves the overall statistical properties of the dataset. This ensures that the released information doesn't reveal much about any single individual, even when combined with other public information. Anonymization, which is another technique, removes identifiers irreversibly and reduces usability. The identification masks data temporarily but risks re-identification through external dataset. Anonymity and other models try to maintain a balance, but each has trade-offs and also vulnerabilities. Pseudonymization keeps identifiers separate from data, linking them via a key. This allows research utility while protecting identity. Pseudonymization of information for privacy in e-health, or PIPE, is a protocol for health data pseudonymization that can securely integrate both the primary and secondary use of healthcare data. It offers traceable anonymity to safeguard the confidentiality of healthcare records. Tools like FHIR pseudonymizers enable safe interoperability, and also another important thing is multi-center pseudonymization that supports broader multi-center studies. Synthetic data is artificially generated to mirror real data sets. GAN privacy refers to the use of generative adversarial networks to protect data privacy by generating synthetic data that mimics real data without revealing sensitive information. Anonymization through data synthesis using generative adversarial networks, or ADSCAN, uses these networks to create usable yet private versions of EHRs. It is a privacy-specific adaptation of GAN architecture designed for medical data like data shared in EHRs. This is a promising path, especially for training AI models without risking real patient data. Software privacy must be continuously validated. In this case, static and dynamic testing tools can identify vulnerabilities. DevSecOps or developing security operations embeds security into the development pipeline, and for mHealth apps, machine learning-based audit tools can evaluate privacy compliance. Privacy and health data security regulations vary globally. In the EU, GDPR sets a strong standard, and ISO standards provide technical guidance. In the US, HIPAA and the HITECH Act address medical data security, and developers must align systems with both local and international frameworks. About interoperability, the FHIR standards supports privacy via consent tags and access rules. And also OpenEHR promotes privacy by design, but doesn't fully meet all GDPR requirements. Both frameworks need customization and policy alignment to ensure compliance. To sum up, privacy is not just technical, it's also ethical and contextual. Our review shows that pseudonymization and synthetic data generation are very promising techniques to preserve privacy, but existing solutions need continual adaptation to match evolving risks and expectations. In this research area, we must go beyond checklists. Privacy strategies should consider the user experience, cultural expectations, and also emerging technologies like LLMs. Collaborative development and context-aware solutions will shape the future of privacy in digital healthcare. And in conclusion, privacy remains a central pillar of digital health. As we move forward to more intelligent and interconnected systems, the responsibility to protect patient data becomes even more critical. Privacy is not only a legal obligation, but also a moral imperative that emphasizes patient trust, clinical integrity, and societal confidence in healthcare innovation. Our healthcare systems must evolve to protect not just data, but the dignity and autonomy of individuals. This means embedding privacy considerations at every stage, from data collection to algorithm design and system development. Regulation, design, and innovation must move together, fostering solutions that are secure, ethical, and also human-centered. Thank you very much for your attention. I'm happy to take any questions, and you can also reach out to me afterwards.
Okay. Someone. Okay. Someone can. Please. Some questions? No one? Okay. Marina, you are talking about the AI models and describe the vulnerability and the potential mitigation and the potential privacy attacks. But we have also about the mitigation strategy for the near future.
I didn't understand the question. You mean that for privacy regulations in LLMs?
Yes.
In LLMs, in our project, we try to use synthetic data like Cynthia to not use the real patient data. So we think that also the integration of pseudonymization and synthetic data can help in integrating LLM models. And it's very important not to use the real patient data in training LLM models.
Okay. Okay, thank you.
You're welcome.
So we can go to the third work that are titled Topic-Based Approach to Evaluate Alternative Solution for GDPR Compliant Smart City Services Implementation. The authors are Lelio Campanile, Mauro Iacono, Michele Mastroianni, Christian Riccio, and Bruna Viscardi. And the presenter is Michele Mastroianni, right?
Good morning to all of you.
Okay.
Okay, I will share the screen. Just a moment. Okay. Can you see the presentation?
Yes.
Yes.
Okay. I will present myself. I'm from University of Foggia. And I work a paper approach to evaluate alternative solution for GDPR compliant service implementation. This is the basic table content of the presentation. First, introduction to GDPR and privacy by design, an overview on the top system method, the description of the proposed approach. The proposed approach is applied as a case study. Case study is a smart city system, smart city monitoring system, and data storage. The alternatives to be compared for best cost performance ratio, and finally results and conclusion. Okay. The GDPR introduces several constraints for ICT system design and implementation, such as privacy by design, privacy by default, a number of other constraints for ICT design and implementation. And there is no standard procedure for following compliance. There is a standard procedure defined by law for following compliance. There are concepts called accountability that must be complained, and the risk of is the risk of ICT. The fines are up to 20 million euro or 4% of global revenue, and operational disruption from the modification to be done to the systems. Okay. Decision making under GDPR is was a business law, and is compliance versus performance and cost, and the risk evaluation must be present in the system design decision, because the risk may several problems by authorities. We can use input from from operating research, like topsis, similar methods, because can hide in another. You can use multi-criteria decision-making problem. Look at TOPSIS. TOPSIS is an acronym for order preference by similarity to ideal solution. The system rank alternatives that are based on proximity to ideal or anti-ideal solution, and is a method that is widely used in multi-criteria decision-making problem, and is widely used also in risk assessment issues. Okay, let's start a little description, short description. Okay, multi-criteria decision-making problem are based on, typically, I have M alternatives and N criteria. This multi-criteria decision-making problem can be expressed in a matrix form. There is a matrix, commonly called the decision matrix, the weight vector. The decision matrix is on the rows are the various alternatives, on the columns are the various criteria, and there are the weights to be applied with the constraint that the sum from 1 to n of all weights must be 1. The main steps of TOPSIS are: the first step is the construction of the decision matrix. The matrix will be normalized. Also, the weight are to be determined or computed or determined by the scientist who construct the system. The first step is construct the weighted normalized decision matrix, and the fifth step is compute ideal and negative ideal solution. After, we can calculate the separation in closeness curves and the the relative closeness to the ideal solution. And finally, we have rank alternatives, the quality of the various alternatives in the system. In our approach, we use the weighting methods called entropy method, in which the value of weights are based on data dispersion, and is appreciated because avoid subjective bias from decision makers. The weights are not decided by humans, but computed from data. You see the formula to calculate the weights with the entropy method. Higher entropy, more dispersion in a criterion, leads to higher weight, indicating criteria importance, so the weights are higher. Widely applicable and simple to compute, and obviously is well referenced by a number of papers using this method to apply to TOPSIS method. There is a limitation, and the computation is purely data-based. There are no observations from managers or experts, so results are sensitive to data quality. If I suspect that data quality is not very high, this is not the best method to use to compute weights. It's only a method to compute weights. Okay. There are two alternatives: negative ideal and ideal alternatives. Ideal alternatives is use all the best coefficient for alternatives. There are two fake alternatives, two formal alternatives that use all the numeric values that are the better, and the negative ideal alternative was the worst values for all the parameters. We apply this method to a case study, smart city data collection. We use the results of the paper which is seated in this slide, estimating performance cost of enabling privacy awareness in data life cycle. We use the computation in this paper. In this case study, there are IoT sensors on roads that capture images, videos, and other information from the human environment, such as moving vehicles, plate numbers, image of people on board, or even people walking on the pavement or crossing the street. This is a privacy-sensitive data process that should be handled with extreme caution. Article 35 GDPR will call it a systematic monitoring of a public accessible area on a large scale. And this is a condition that leads to a cautious data processing due to particular condition of the system. The system in the paper I cited, the system has been simulated. The system simulated with Markov chains. There are the action diagram of the system. The system as is a simple chain, collection, preparation, analysis, storage, and share and publish. The system modified to be GDPR compliant have several modifications, deep modification, in particular in the phase of analysis and the phase of storage, to ensure that the privacy will be complained. The GDPR will be complained to GDPR. Okay, in order to evaluate, to compare the as-is and to-be system models, we use TOPSIS and have three evaluation criteria. The first criteria is the cost of the system. The second criteria is the average response time. The third criteria is the rate of images standing in non-safe zone, used as a
Sorry, Michele, we cannot hear you now. Michele, can you hear us? Someone can hear us? Can hear us? No. No, Michele, we cannot hear you now. Can you hear us? Try now.
Okay, we
You can
hear me?
continue. Michele, can you hear us?
Yes, I can hear you.
Yeah, you can continue.
Okay. Okay. I would say that can propose a top-based approach. We aim to compare the as-is and to-be system models. This is the first and second diagram on the previous slide. The evaluation criteria are cost, average response time, and rate of image staying in a non-safe zone. So images that are not encrypted and running in some part of the system. This rate is used as a proxy for privacy risk. And the system obviously have been simulated under equal workload. The alternatives, we use two alternatives for as-is system. The original system is as-is1, designed without concern about GDPR. The alternative as-is2 is the original system with cost increases due to a fine committed by the personal data processing authority. And other criteria are the same value of the previous. Is only to maintain separated the system as is and possible fines, and the system to be designed to be compliant to the GDPR. The decision matrix, the cost of as-is1 and to-do solution is computed with a ratio of 4:1. This is done by some paper in literature and an evaluation of the systems to be realized, to be implemented, and the amount of the fine due to the GDPR violation can double the cost of the whole system. So the cost of as-is2 is the double of the cost of as-is1. The response time simulated, the data of the response time image rate as are taken from the paper, the previous work we cited in literature, our previous work. The response time is as-is1 and as-is2 43.86 transaction per second. To do is 43.86 seconds, to do 66.82. Images rate simulated is 240 for as-is1 and 2, and for to do is 77 images rate. This is the decision matrix. We see as-is cost, as-is1 cost 1, cost 2 cost 4, and the other values. We see the normalized matrix and the weights computed with the entropy method, and the final score in which there is a to-be score
the highest score .687, and this is much lower. So with this, with the case study, the best option, the best alternative is to be alternative. We see the results also in a bar graph. You see in the red bars. The red bars are the case study you're observing to be so the GDPR compliant system are evaluated as the best system, the best alternative. The alternative is more near to the ideal alternative, and the two values are lower. We compute another time TOPSIS system using equal weights, using for the weights equal values of 0.33 values. There are light blue values. In this case, the weights are not computed by entropy method. The entropy method give the higher value to the IMG image safe value and the lower value to response time. But with using equal weights of 0.33, we can see the blue bars, light blue bars. Light blue bars give another kind of results in which ASIS1 is the best, but if I evaluate ASIS1 and I think that are possible fines by the regulation authority, the 2B alternative is even better than ASIS. This is represented to 2B is higher than ASIS2. The results in case of entropy computed weights, the best alternative is the GDPR compliant solution. In case of equal weights, the to-do solution is not the first, but have a score higher than the ASIS2. Then is the original solution in which the costs are being increased due to possible fines. In case of real possibility of a fine, the best solution is even the privacy-aware solution. Conclusion. In conclusion, we can say that TOPSIS might help balance privacy cost and performance, and in the case study examined, the 2B solution outperforms despite higher initial costs. Future work will split in two main directions: redact a more precise design of the alternatives with the aim of better compute cost and other values, and define other quantitative metrics for privacy purposes to test a more comprehensive analysis using TOPSIS. Okay. I finished my presentation.
Thank you, Michele.
Okay.
There are some questions. No. So, Michele, do you think that TOPSIS-based approach can be used directly to the public authorities or designed for, I don't know, urban systems?
I didn't understand the question.
Your TOPSIS approach can also use directly to the public authorities.
Yes, can be used also by is a well-known multi-decision, multi-criteria technique, and can be used also by the authority to evaluate. The evaluator in particular may be evaluated evaluate and validate some data given from firms, in example, may be used by authority.
Okay, thank you.
Okay.
So we can go to the last virtual presentation. The title of the work is Toward Deleted Environment Monitoring of CO2 and Air Pollutant in Southern Italy. The authors are Lelio Campanile, Luigi Piero Di Bonito, Fiammetta Marulli, Antonio Barzanella, and Rosanna Verde. The presenter is Lelio Campanile. So
Hello,
you can
there we are. Can you hear me?
Yes, you can hear.
Okay, I just start to share the screen. Okay.
Okay, Lelio, you can start to share the screen.
Okay. Okay, just let me time to share the screen because I have an issue here. Okay, just 1 second, please.
So, Michele, I think that you are sharing your screen now. No. Sorry, Lelio, we have some problems. Okay.
Now we can see your screen.
Okay, let me to start my presentation. Okay, now everything should be fine, right?
Yes, we can see your presentation.
Okay, let me to start. Okay, good morning to everyone, and let me to before to start my work that is toward price aware environment monitoring of CO2 and air pollutants in Italy. Let me to thanks my co-author that they are Luigi Piero Di Bonito, Fiammetta Marulli, Antonio Balzanella, and Rosanna Verde. So, going to the agenda of this presentation, and before diving into the details, let me briefly summarize what this work is about. Okay, in our study, we want to tackle some of challenges in environment sustainability and public health. And the problem in this field is that sometimes we have a lot of data sources, but these data sources are not being well joined between us. So in our works, primarily we want to create a comprehensive multi-source data set that merge different data set, and for do these things, we used a methodological workflow. So then we just performed an analysis of the result of the merged data set, and we also created an environmental vulnerability index that is a kind of index following analysis. Okay, so go to next. And why this work and why in southern Italy? Okay, as you know, the greenhouse gas emission and air pollution are, the most critical challenge in environment sustainability and public health. And this is especially true in regions like southern Italy, but not only, of course, in southern Italy, but in this kind of region which combine complex socioeconomic structures with different complex and diverse geographic features. So despite their vulnerability, these areas lack of high resolution data that making it hard to design this target intervention. So our work try to address this gap by creating a multi-source dataset to support analysis and policies decision in this area. Okay, so what are the primary objects? So the primary goal of these works is to create a merged data set, and then to perform a first analysis of this merged data set to try to get some good information about this data set. And the final goal should be to have this information as a support to make decision by public authority and other person that will be involved in this process. And just to clarify, where are the data sources that we use in our works? We rely our works mainly on these three datasets that you see in this slide. The EDGAR version 8.1 database that provide a long-term data on CO2 and not only on CO2, but have information about a lot of other air pollutants, and with a high spatial resolution. Okay, EDGAR mainly is a European project that uses satellite information to get data about air pollutants. Then we merged with some demographic, urbanization, and morphology information by ISTAT database. ISTAT is the Italian statistical agency. And finally, we add another database that cover artificial surface and basically the land, the kind of land, so artificial surface, forest, shrubland, grassland, and other information about the surface, the geography of our area. How we work? Okay, we use it the methodological workflow depicted in this figure, in this diagram, that provides a clear overview of our workflow. Okay, on the top here you can see the three main data streams that we want to integrate. So the emission data from EDGAR, basically, the demographic data from ISTAT, and the morphology data from the last data set. Then this feed into a unified data processing block, that is the data preprocessing, where handle cleaning and try to harmonize the scale of all this information and a kind of spatial alignment. Okay, please note that in this phase, with this dashed arrow, connecting the privacy risk and mitigation framework to the preprocessing stage. And okay, after this data preprocessing, the new dataset is created, and then on this new dataset, we can construct our new index, that is the AVI index, that is Environment Vulnerability Index, which try to aggregate information about emission, urbanization, and population data in a kind of composite metric. Okay, so go to the next. After merging the data and the first data cleaning, one task that we have to involved in is about data refinement, because the grid-based emission data are not clear. I mean, the data set that we use are not well formatted with all the data, but they are with irregular boundaries, and especially in irregular data set. I mean, sometimes we have null value and some things of that. So we aggregated demographic and land used emission using the kind of grid cell. So this allowed us to compute population density, total land area, and other metrics, and we try to reduce everything to a single scale to make it more easy to process in the next works. Okay, just to give you an example of result of our works, this table is a kind of example of the final result, in which we have the grid cell that it's represented by coordinate. So it is a real, square on the map, and the CO2 emission, the carbon balance, and then the carbon status. Of course, we can see here that carbon status is surplus or deficit, basing on the difference between emission and absorption of CO2. Okay, the special exploration revealed some expected patterns, and in the area that we analyzed, so the southern Italy area, we see that the major hotspots for CO2 emission are located near urban and industrial center. That is more or less expected because the urban city as Naples, Palermo, and Bari in the southern Italy, that are the most important city in the southern Italy, are the major hotspot for CO2 emission. And of course, in other hand, the rural inland area, especially, I don't know, for example, in southern Calabria, that is a Italy region, or Puglia, then we have much lower emission. Okay, this could be, it is something of expected, but it reveals some interesting information, because we have in this area a very high heterogeneity underscored for specific location intervention. And other important information and interesting things we can get from the correlation analysis. Okay, we just performed a person correlation matrix between the different information on our data set, and we see that, not completely as expected. We found only a weak correlation between emission, population, and land cover. That suggests something that is not well expected, and we have a lack of correlation, a lack of high correlation between population density or vegetarian cover. So there is something of interesting from this analysis and from this data set merging. Okay, then we try to do something more, and we just performed a very easy and simple regression analysis. Please let me to remember that this part is not the goal of these works, but we just performed this to try to get some more information. And we got that we have the relationship in the figure. On the left, we can see the relationship between population density and CO2 emission. And in the figure on the right, you can see the relationship between tree cover and CO2 emission. And in both the result, we just indicate that industrial infrastructure and transportation network are dominant factor. Okay, in this way, please let me to see that this graph has a different concentration of things, because we have some outlier in high place of this graph. So okay. Nevertheless, this is not the final goal of this work. So it could be interesting to start to perform some more complex analysis on this data. Then an information that we have to assess sustainability is that we calculate a carbon balance metric that is, something so very important, that comparing the emission to the estimated absorption capacities of local vegetation. Okay, so with this kind of balance, we just to check the difference between the CO2 created and emissioned by a person, industry, and vehicle. less than the CO2 that the tree, I mean the forest and the shrubs and the grassland can able to absorb. Okay, so to do this analysis, we used standard observation rates that we find in literature that are about 10,000 of CO2 for hectare for forest, 3 for shrublands, and 1 tons of CO2 for grassland. And so this allowed us to classify areas into 2 different classes that are carbon deficits and carbon surpluses. Okay, at the end, to try to create some things of novel in our works, we create an interesting, I mean, of course, in our opinion, index that try to summarize all the insight that we found during our dataset analysis. And this index is the Environment Vulnerability Index that integrate the CO2 emission, I mean about intensity of CO2 emission, the urbanization level, the population density, and got all this information inside one easy to read metrics that is this kind of environment vulnerability index. To do better, we normalize this factor in a scale between 0 and 1, so that's, I mean, can help to use this index for and to read this index in the right way. So let me to conclude, and our site provided a robust and multi-source dataset that try to enable detailed assessment of CO2 emission and absorption relative to demographic information, land use factor, and urbanization factor in southern Italy. We just created a new index, and okay, for the future works, we of course try to integrate more machine learning and real-time monitoring, because one of the future work to be to use real-time IoT sensor, for example, to feed our dataset with new information, and using in near real time this information to create and to update our index, but also to create a new analysis, more complex analysis on this dataset that could be involve machine learning and deep learning algorithm. For the future works, in this paper, we anticipated trying to preserve privacy using, I mean, because when you are using IoT devices, you just have to take care of privacy of people. Of course, in our works, there are no personal data in explicit manner, but we just want to, as a future plan, to create a privacy-aware analytics. And could be, for example, if you want to use some information from a personal house of people, because a lot of information we can try to use and getting this information from IoT devices in the house of people, but to use this kind of information, just let me to explain these things, because we have a lot of IoT devices that nowadays we can use. Do you think, I don't know, the Netatmo devices or something similar devices, but to be fair with people that can give us this information, we just to improve the privacy-aware part of our works, and in the next future we can try to increase privacy using, for example, differential privacy task, differential privacy technique to improve this part. And we also try to use a DPIA for regulatory compliance on GDPR. Okay, Thank you for your attention, and if you have any question, I can answer your question. Please, thank you.
Thank you. Thank you. Thank you for your presentation. There are some questions. There are some questions. Just for one question, if you want, you can ask. No? Okay, so I think that is better to go to the last one. So thank you, Lelia, for your presentation.
Okay.
If someone wants to send a question, there are email of Lelia. So we have the last work that are fast saving algorithm for solving large scale Euclidean CVLPS. And the author that presents this work is Kenzie Kawasaka. So Kenzie, the floor is yours.
Okay.
You can start.
Okay. Okay. Just one also to share the screen on the GC platform. So okay, so now I'd like to start my presentation. Yeah, this is stuck on the first one, so let me have. Sorry for the delay. No, because now we are looking also the side note. It's fine. It's fine. Also, if they say because they are seeing also the sidebar. Okay. Yeah. Okay, so I would like to my presentation. My name is Kenji Kanazawa from University of Tsukuba. So let me introduce the capacity safe vehicle routing program. This is an NLP hard combinatorial optimization program whose goal is to find a set of delivery routes starting and ending at a depot that cover all customers with multiple vehicles with minimum total distance of the vehicles. And as constraint that the total load of delivery items along each route does not exceed the capacity of vehicles. Euclidean CVRP, which is the target of this research, is a variant of CVRP where the distance is adhered to the Euclidean metric. Clark-Wright saving algorithm is a representative heuristic algorithm for solving CVRP. Given n distinct customers, it initially generates n distinct delivery routes, each linking the depot and a single customer. In this example, the total distance of visiting customer 1 and customer 2 is 11.4 and 21.0 multiplied by 2 because the vehicles must travel each customers and depot back and forth. The algorithm then initially iteratively selects two distinct delivery routes to merge to a single route
guided by saving value without violating the vehicle's capacity restriction. Saving value stands for the distance reduction by merging the two routes by linking two customer nodes. When merging routes for customer 1 and customer 2 in this example, the total distance for the new delivery route becomes 11.4 plus 28.1 plus 21. So the saving value in this case is the differential of the distance before merging and after merging, which corresponds to 4.3. CW algorithm involves deriving the saving values for all possible pairs of the initial routes and sorting the resulting n-squared saving values in descending order so that it preferentially selects good pairs with greater distance reductions for merging, which is the most computationally intensive part in CW algorithm. The time complexity is order n squared log n when using standard comparison-based sorting algorithms such as quick sort or merge sort. Therefore, the execution time rapidly grows as the number of the customer increases. This is a literature review. Arnold proposed a modified version of CW algorithm called CW100, which constructs a solution only considering saving values between each customer and its 100 nearest nodes. It requires 3 to 34 seconds to solve instances with 3,000 to 12,000 customers on this CPU, including post-optimization via link-Kanihan heuristic. Guerriero proposed a GPU acceleration of CW algorithm, in which they optimizes the distance and saving value calculation by parallel processing on CUDA core, and also introduces a tabu list to skip the superfluous saving values during the solution construction. But they didn't address the inefficiencies in sorting the saving value, thereby leading to limited performance gain in solving large-scale CPU outputs. Specifically, they require their system needed 183 seconds for the problems with 30,000 customer nodes. Our approach, we propose a variant of CW algorithm for efficient solving Euclidean CPU outputs. Our approach discretizes the saving values utilizing approximate Euclidean norm, which enables calculating the saving values in only integer arithmetic and also enables sorting the saving values using distribution-based linear time sorting algorithms such as counting sort or pigeonhole sort. Thereby, the time complexity of our approach can be reduced to order n squared. The experimental results showed our approach can obtain the feasible solutions for the problems up to 30,000 customers in 2.88 seconds on average, preserving the solution quality which is corresponding to 6 times speed up over the original CW algorithm. Detailed procedure of the CW algorithm. The input of the algorithm are the set of nodes, and including their locations of depots and customers, and the set of items load for each customer and capacity of the vehicle, the capacity of the vehicles. The algorithm first generates a set of delivery route by connecting each customer node and depot on which vehicles travels back and forth. It then calculates saving values for each pair of customer nodes as mentioned in previous. Saving values stand for the reduction of the travel distance when merging two routes by connecting two customer nodes, which corresponds to the differential of the travel distance before and after merging. Obtained saving values are sorted in descending order. It then merges two distinct routes with larger saving values preferentially under the constraints that the total delivery item loads along the merged routes does not exceed the vehicle's capacity. In this example, it attempts to merge the customer 2 and 3, the root for customer 2 and 3, because they have the largest staging values. They can be merged because the total delivery item loads 5.1 tons does not exceed the vehicle's capacity loads. Next, it attempts to match the route for customer 4 and the route for customers 2 and 3, but it's infeasible because the total item loads exceeds the load of the capacity of the delivery vehicles. The algorithm continues like this. This is the result in this example. As already mentioned, the time complexity becomes O times squared log n when using standard comparison-based sort, like merge sort or quick sort. To further enhance efficiency, our approach have modified the original CW algorithm so that it can apply distribution-based sort algorithms such as counting sort or pigeonhole sort. The time complexity of counting sort or pigeonhole sort is order m plus k, where m is the number of the elements to be sorted and k indicates the range of the sort key values. The time complexity of CW algorithm can be reduced to order n squared when m is enough larger than k. However, counting sort and pigeonhole sort can handle only non-negative integers. So saving values must be non-negative integer, which is necessary to be discretized and offset by their minimum value when there exist negative saving values. There are several options for discretizing the saving values. The first one is to perform all steps to derive the saving values in floating point and then rounding to integers. The second one is to input the CVRP coordinates and calculate Euclidean distances in floating point values and round them to integers. The third one is to round coordinates of the customer and depot nodes on reading the CVRP instances and perform all subsequent process in integer arithmetic. This is the least computationally intensive, but it requires alternative way to calculate Euclidean distance by only integer. To address this, our approach employs approximate norm proposed by Chaudhry. This is the Chaudhry's approximate norm. In Chaudhry's approximate norm, LP norm of n-dimensional vectors x and y is formulated as linear combination of L infinity norm and L1 norm, like this formula. Substituting 2 to small substituting 2 to small p and small n in this formula, we can obtain approximate Euclidean distance in 2D space formulated like this. In two-dimensional space, L infinity is expressed as this one, which is calculated by subtractions, absolute operations, and comparison for integer operands. And also, L1 can obtained by subtractions, absolute operations, and additions for integer operands. L2 norm is the linear combination of L infinity and L1 over 2, and division by 2 corresponds to right shift. So by using approximation norm by Chaudhry, we can calculate approximate Euclidean distance by only lightweight integer arithmetic. The evaluation results. We coded our approach by using C language and compiled by using ZCC with O3 option. Then we evaluated our approach with respect of suitability for using distribution-based sort, solution quality, and execution time using two benchmarks with apart of which was benchmark with 500 to 1,000 customer nodes and Arnold's benchmark with 3,000 to 30,000 customer nodes. Evaluation platform was this one. Suitability of using distribution-based sort. Specifically counting sort and pigeon hole sort. This table shows the part of the results. Please see the proceedings for the full results. As mentioned in previous slide, time complexity of counting sort and pigeon hole sort is order m plus k, and m corresponds to the number of the saving values and k, the range of the saving values. As can be seen in the tables, m is larger enough than k in all tested cases, so it is suitable for using counting and for pigeonhole sort. The time complexity virtually becomes order n squared in our approach. This is the solution quality. The first table compares the cost, namely the total travel distance in best case, cost obtained by the original CW algorithm, and the cost obtained by our approach. This is the total average relative gap between the best cost and each approach. Deterioration has been observed, but it's very little. Finally, we show the execution time result. The table labeled 0 is the time by the CW algorithm, the original CW algorithm. The second one is the CW algorithm, but the saving value was discretized. This one is our approach by using counting sort. I will skip this slide. Our approach with counting sort outperforms the CW algorithm without discretizing and saving values in all the tested cases, owing to the order of magnitude speed up in sorting. The average speed up over the original algorithm is 2.6 times for Ushua's benchmark and 6 times speed up for Arnold's benchmark. On the other hand, our approach with pigeonhole sort showed the limited performance gain due to the overhead caused by memory allocation for acquiring the pigeonhole workspace for storing the element while sorting. I will skip this slide. Conclusion. We proposed a fast savings algorithm for efficient solving large-scale Euclidean CPRPs. Our approach discretizes the saving value utilizing Chaudhry's approximate norm, which can derive approximate Euclidean distance by only lightweight integer arithmetic, thereby which makes it enabled to use the distribution-based linear time sorting for sorting the saving values. Experimental results showed our approach achieved 6 times speed up over the original CW algorithm, preserving the solution quality for large-scale Euclidean CPRPs. The presentation is all.
Okay,
Thank you for your attention.
So, what do you plan for the future work?
I plan to implement on hardware. I am a hardware researcher, so at first I wanted to parallelize the CW algorithm. So that's why the main reason for exclude the floating point calculation.
Okay. Thank you.
Thank you very much.
Thank you.
So the session is finished.
Okay. Now there is a plenary session at the conference room, maybe at the upstairs floor, and at 11 o'clock. Maybe it will start 15 minutes late. Now, if you want to enjoy the coffee break, thank you for your participation. And again, I apologize for all the technical issues that we have experienced, but the first session is always a bit tricky. So thank you for your patience. Thank you for your contribution, and see you later.
Thank you. Bye.
Bye.